Welcome back to Bite-Sized Breakthroughs, where we explore the latest and greatest in the world of AI. Today, we're diving deep into a groundbreaking paper from Metafair that takes the Segment Anything model to a whole new level. Segment Anything Model 2, or SAM2 for short. It's fantastic to have Dr. Paige Turner joining us. Paige, you're a leading expert in visual segmentation, and you've been closely following this research. Can you give us a brief overview of what SAM2 is all about?
Absolutely, Alex. SAM2 is all about taking the power of visual segmentation beyond static images and into the dynamic world of videos. It's a foundation model, meaning it can be trained on a massive data set and then applied to a wide range of tasks without needing to be retrained from scratch.
So it's essentially a versatile tool for identifying and isolating objects, not just in pictures, but in videos too. That sounds incredibly useful.
Exactly. And it gets even more interesting when you consider how SAM2 achieves this. It introduces a concept called streaming memory. This memory acts like a short-term memory for the model. It allows SAM2 to keep track of objects across different frames in a video, even when they move, get partially hidden, or reappear after being fully obscured.
That's fascinating. So instead of processing each frame in isolation, it's actually learning the context of the video and using that information to improve its predictions. This seems like a huge leap forward in video segmentation.
It truly is, Alex. And to make this possible, the researchers needed a vast dataset to train SAM2. They created a new dataset called the Segment Anything Video Dataset, or SAV for short. This is the largest video segmentation dataset ever assembled, with 50.9 thousand videos and over 642,000 masklets. It's incredibly diverse and covers a wide range of everyday objects, scenes, and challenges.
That's a huge amount of data. What's remarkable is how they actually collected all this data. They designed a novel data engine that actually uses the model itself to help annotate videos. Can you elaborate on how this works, Paige?
It's a clever and efficient approach, Alex. They started by using the original Segment Anything model, SAM, to help annotators manually segment objects in each frame of a video. This, of course, was a slow process, taking an average of 37.8 seconds per frame. Then they introduced SAM2 into the annotation loop, first only accepting masks as prompts. This significantly sped up the process, reducing the average time per frame to 7.4 seconds. Finally, they used the fully featured SAM2, which accepts points, boxes, and masks as prompts. This allowed annotators to provide fewer corrective clicks and further improved efficiency, bringing the average annotation time down to just 4.5 seconds per frame.
So they used the model itself to make the annotation process faster and more efficient, and then they used the annotated data to further improve the model. This is a really neat example of a self-reinforcing loop. It's almost like a virtuous cycle of improvement.
Exactly, Alex. And it shows the power of using AI not only to solve problems, but also to improve the very data it uses to learn. This is a key innovation in the paper.
It's fascinating how they were able to create such a massive data set, and it definitely highlights the importance of good data in training powerful AI models. Now let's dive into the technical details of SAM2 Page. You mentioned streaming memory. Can you give us a more detailed explanation of how it works in the model?
Sure, Alex. Imagine a video playing frame by frame. As each frame comes in, the SAM2 model processes it through an image encoder. This encoder uses a transformer architecture called Hiera, which has been pre-trained on a massive dataset of images. Hiera is really good at extracting features from images, and it's used to create a set of unconditioned tokens representing each frame. Think of these tokens as a compact representation of the information in the frame. So we have these tokens for each frame, and SAM2 needs to figure out how they relate to each other over time. That's where the streaming memory comes in. The memory attention module is where the magic happens. Okay, let's break down memory attention. It's basically a stack of transformer blocks that perform two types of attention: self-attention and cross-attention. Self-attention allows the model to analyze the relationships between tokens within a single frame, figuring out how different parts of the frame relate to each other. Cross-attention is where the temporal information comes into play. It allows the model to compare the tokens of the current frame with the tokens stored in the memory bank. The memory bank is essentially a collection of memories from both prompted and unprompted frames. It's like a short term history of the video. The model can then use this information to better understand how objects are moving and changing throughout the video. This memory bank also stores object pointers, which are like short descriptions of the objects being segmented. These pointers provide a high level semantic understanding of the object, helping the model to better connect the features across frames.
So, the model is not just looking at the current frame's information, but is constantly comparing it with the previous frames and their object descriptions. It's like having a memory of what happened before, which helps it make more accurate predictions.
Exactly, Alex. And this is what makes SAM2 so effective at handling challenging scenarios like partial occlusion and object reappearance. It can use the memory to predict what's happening behind an occluding object and even recall an object that was fully hidden in previous frames.
Now, let's talk about how the model is trained. You mentioned that it's trained jointly on images and videos. How does this joint training help improve performance?
The joint training allows the model to learn generalizable concepts that apply to both static images and dynamic videos. It's like teaching the model a common set of rules for understanding objects that work across different visual domains.
So, it's not just learning how to segment things in videos, it's also learning the fundamental principles of object segmentation in general, and it can apply that knowledge to both images and videos. That's a really clever approach.
That's a great point, Alex. And the way they train the model is actually quite similar to the interactive experience a user would have. During training, they simulate an interactive setting where the model receives prompts and corrective clicks. The model learns to predict the correct masklet for each frame, even when the object is partially occluded, moves, or disappears. This interactive training helps the model become more efficient and accurate when responding to user input.
This all sounds incredibly impressive, Paige. Now let's talk about the results. What are the key findings of the paper in terms of SAM2's performance?
SAM2 truly shines in its performance. In video segmentation, it achieves better accuracy with 3 times fewer interactions compared to previous approaches. It's also a lot faster than the original SAM, with a 6x speedup. These results are quite significant, especially when you consider the complexity of video segmentation.
Those are impressive numbers, Paige. It really seems like SAM2 is pushing the boundaries of what's possible in video segmentation. And they even went a step further to assess its fairness across different demographic groups.
Yes, Alex. They conducted a fairness evaluation using the EGO EXO4D dataset, focusing on segmenting people. They looked at gender and age groups. They found minimal performance discrepancies when using 3-click prompts or a ground truth mask. However, with 1-click prompts, there was a slight difference, but this was attributed to ambiguity in the prompt, as the model sometimes segmented a part of the person rather than the whole person. This highlights the importance of carefully considering prompt ambiguity and how it can impact model performance, especially in real-world applications.
That's a great point, Paige. It emphasizes the need to be mindful of potential biases and fairness issues when applying any AI model, especially one as powerful as SAM2.
Absolutely, Alex. It's crucial to assess fairness and mitigate potential biases in any AI system to ensure responsible and ethical use.
It seems like we've touched on some of the major breakthroughs and innovations in the paper, but I'm sure there are still some details that our listeners might be wondering about. Professor Spectrum, you've been working in computer vision for years and you've seen the evolution of these segmentation models. What are your thoughts on SAM2, especially compared to previous approaches?
Well, Alex, I'm extremely impressed with the work on SAM2. It's a significant step forward in visual segmentation, especially in the video domain. As Paige mentioned, the streaming memory architecture is a clever and efficient way to handle the temporal aspect of video, and it's clear that they've put a lot of thought into the data collection process. The SAV dataset is a valuable resource that will benefit the entire research community. I think what sets this research apart is its focus on the practical aspects of segmentation. They haven't just created a model that performs well on benchmarks, They've addressed the challenges of data collection and annotation, which are often overlooked in research. This approach ensures the model can be readily deployed and used in real-world applications.
That's a really insightful point, Professor Spectrum. So you're saying that while the technical advancements are impressive, it's the practical aspects that make this work truly groundbreaking. It's not just theoretical, it's something that can actually be used in the real world.
Absolutely. And the fact that they've addressed fairness concerns by conducting a demographic evaluation is also commendable. It's something that's becoming increasingly important as we deploy AI in more sensitive applications.
You've touched on some really important points, Professor Spectrum. I think it's crucial for researchers to consider not just the performance of their models, but also their real-world implications and potential biases. Paige, are there any limitations of SAM2 that the authors themselves acknowledge or that you've identified?
Of course, Alex. As with any AI model, SAM2 has its limitations. The authors highlight that the model can struggle with object segmentation across shot changes, particularly in complex scenes or extended videos. They also note that the model might lose track of objects after long occlusions or in crowded scenes, which might require user intervention to correct errors. Additionally, SAM2 has some difficulty accurately tracking objects with thin or fine details, especially when they are moving quickly. While the model can handle multiple objects simultaneously, it processes each object separately, which could potentially be improved by incorporating shared object-level contextual information. Finally, the data engine currently relies on human annotators for quality verification and frame selection, which could be further automated for improved efficiency.
Those are all valid points, Paige. It's good to remember that even with a model as impressive as SAM2, there are still areas for improvement. These limitations highlight the ongoing need for research and development in this field.
Absolutely, Alex. And the authors themselves suggest several promising future directions. They plan to incorporate more explicit motion modeling into the model to better handle complex motions and occlusions. They also envision mechanisms that allow for inter-object communication, enabling the model to leverage shared context across multiple objects. They are also looking into automating the quality verification and frame selection process in the data engine. And finally, they are exploring alternative memory architectures and attention mechanisms to potentially improve the model's performance and efficiency.
So it seems like there's a lot of exciting research ahead for SAM2. Professor Spectrum, can you talk about the potential impact and applications of this technology? Where do you see SAM2 fitting into the bigger picture of computer vision and AI?
SAM2 has the potential to be truly transformative in several areas. In AR/VR, it could revolutionize the way we interact with virtual objects by allowing seamless integration with the real world. In robotics, it could help robots better perceive and manipulate objects in complex environments. In autonomous vehicles, it could enhance scene understanding and navigation by providing precise object segmentation and tracking. The possibilities for video editing are also immense, from background removal to object replacement and more. Even in medical imaging, where precise segmentation is crucial, SAM2 could have a profound impact, aiding in diagnosis and treatment planning. The applications are truly vast and exciting.
This is a really great overview, Professor Spectrum. It sounds like SAM2 has the potential to contribute to a wide range of important technologies and applications. It's quite remarkable how far visual segmentation has come. Paige, any final thoughts on this groundbreaking research?
I think this research really pushes the boundaries of what we can achieve in visual segmentation, particularly in the realm of video. The combination of the innovative streaming memory architecture, the comprehensive SAV dataset, and the model-assisted data engine is truly remarkable. It's clear that SAM2 is a significant step forward in the field, with vast potential for real-world applications. It's exciting to see where this technology will take us in the future.
Thank you both for this fantastic discussion, Paige and Professor Spectrum. I'm sure our listeners are eager to explore this research further. We've covered a lot of ground today, but the main takeaway is that SAM2 is a powerful new tool for visual segmentation that can handle complex scenes, dynamic objects, and even long videos. It's fast, accurate, and has the potential to transform a wide range of applications. Be sure to check out the links to the paper, the dataset, and the demo on our website. Thanks for tuning in, and stay tuned for more exciting breakthroughs in AI.